Welcome back students in the third part of pressure. In this video, I will discuss about atmospheric pressure, measurement of atmospheric pressure and liquid pressure. With that, some consequences related to atmospheric pressure and liquid pressure. So let's start. Atmospheric pressure. What is atmospheric pressure? The pressure exerted by our atmosphere on the Earth's surface is known as atmospheric pressure. Or you can say the thrust exerted per unit area due to the column of air is known as atmospheric pressure. It is also called as barometric pressure. At sea level, it is maximum, which is around to 10 to the power 5 Pascal. Atmospheric pressure used to change from place to place. It depends on temperature as well as altitude. So why does the pressure changes at high altitude? The basic reason you can say that at high altitude, the air is comparatively thinner than to that air which is near to the sea level. Let's understand about this with an animated video.
We are surrounded by air from all the directions. This envelope of air around us is what we call atmosphere. Does air also exert pressure on objects on the Earth? In our previous video, we studied that the liquid exerts pressure in all directions. For example, here we have the water in a beaker. Due to gravity, this water is pulled down towards the Earth. If we divide this water into different layers, then each layer is being pulled down by the Earth. Due to this pull, water exerts downward pressure and this pressure is uneven throughout. That is, the bottom layer experiences more pressure than the top layer. This is because the weight of water above the bottom layer is more, and the pressure decreases as we go upwards. In fact, we saw that the water exerts pressure in all directions and not only in the downward direction. One more thing that we studied about the liquid pressure is that at any point in a liquid, the pressure is the same in all directions. That is, if I take any point here in this water, the pressure exerted by water here is the same in all the directions. Air also behaves in the same way. Just like water, air is also being pulled down by the Earth's gravitational force. This force applies pressure on the air in the downward direction. The pressure exerted by air is called air pressure or atmospheric pressure. Did you know that the atmosphere is divided into different layers? The atmosphere is divided into 5 layers, namely the troposphere, stratosphere, mesosphere, thermosphere and exosphere. The pressure in the troposphere, which is the bottommost layer, is higher than the pressure in the layers above it. And I'm sure you can guess the reason why. This is because the weight of the air above the troposphere is greater than the weight of the air above, say, the stratosphere. The air pressure also acts in every direction and not only in the downward direction. And finally, just like the pressure in liquids, the air pressure at a particular height above the Earth's surface is same in all directions. That is, if I take these 2 points at the same distance above the Earth's surface, then the air at this point will exert an equal pressure in all the directions, just like the air at this point. Let's look at an interesting graph now. A graph which represents pressure at a particular altitude. The graph also represents how the pressure varies from layer to layer. The troposphere layer is closest to the surface of the Earth and the pressure in this layer goes up to 100,000 Pascal, where Pascals, represented by PA, is the SI unit of pressure. This is massive pressure. This pressure pushes and pulls the object on the surface on the Earth. For example, if I take a table with the upper surface of 1 by 1 meter, the pressure exerted by the air on the table in the downward direction is greater than 1 lakh pascals. This is equivalent to 10 cars being put on this table. Yes, 10 cars. I know what you must be thinking. Why doesn't this surface collapse under this huge pressure? How does it handle such massive pressure acting down on it? A little while ago, we said that the pressure exerted at points above the Earth's surface is equal in all directions. So the pressure at every point on the table is the same in all the directions. That is, if downward pressure is pushing the table surface with a great force, then the upward pressure is also pushing it in the upward direction with the same force. Both the forces are balanced and the table does not collapse. As I said, pressure is not only acting in these two directions, it is acting on the surface in all the directions. Pressures acting in opposite directions cancel each other out. Here is one cool experiment that you can also perform at home. Take a plastic bottle filled with water. Take a cardboard paper and place it on the open end of the bottle like this. Hold this paper with your hand so that it does not move from its position and invert the bottle. Now let go of the paper. What did you see? The cardboard paper sticks to the surface. Why is it held to the surface? It is held to the surface because of the air pressure that is pushing the paper in the upward direction. The upward air pressure is sufficient to counter the downward push exerted by the water. Now make few holes in the bottle at its base. What happens now? Why did the paper fall off? Did the upward pressure on it stop acting or did it reduce in the value? No, it didn't. The upward pressure on it by the air remains the same, but the downward pressure increased in its value. When we made holes in the bottle, we allowed air to flow inside it from the top. The air from the top started exerting pressure on the water. The combined pressure of water and air from top could easily overcome the pressure exerted by air from the bottom. Hence, there is net force acting on the paper in the downward direction. That is, there is more pressure in the downward direction. That is the reason why this paper gets detached from the surface.
Through the video, I hope you had understood about atmospheric pressure. Now let's see how we can measure the atmospheric pressure. The instrument which we use to measure the atmospheric pressure is barometer. A barometer can be classified into three basic kinds, that is, a simple barometer, a Fortin's barometer, and aneroid barometer. Among these, the simple barometer and Fortin barometer uses mercury to measure the atmospheric pressure, whereas aneroid barometer doesn't require any liquid to measure the atmospheric pressure. Therefore, oftenly it is said that simple barometer and Fortin barometer is a liquid barometer. You can understand more about barometers through my separate video related to barometers. Now let's see how we can measure the liquid pressure. We had already understood the phenomena of liquid pressure. Now let's see the instrument which we can use to measure the liquid pressure, that is a manometer. Here we are having a manometer which we use to measure the liquid pressure. Manometers uses the atmospheric pressures principle to measure the liquid pressure. Let's understand the working of a manometer with an animated video. Here we have a manometer which used to measure the liquid pressure. It is consists of a glass U-tube which is fixed to a stand with a scale and it is half filled with water. One end of the U-tube is open and the other one is attached with a thistle funnel through a flexible tube. The mouth of the thistle funnel is covered with a light, thin rubber skin. When the thistle funnel is kept in open air, only atmospheric pressure acts on it. This is equal to the pressure acting on the open end of the U-tube. Therefore, water level in the two sides of U-tube remain the same. Now, dip the thistle funnel in the bucket of water. The liquid pressure acts on the rubber skin. As the liquid pressure on it increases, the water level in A pressure go down and B increases up. The difference in the water level can be read on the scale. This is the measure of the pressure exerted on the rubber skin. Now you can use the formula rho Hg to calculate what is the pressure exerted by the fluid over there. Here we have some of the consequences related to atmospheric pressure which we experience in our day-to-day life. Sucking a drink with a straw, filling a syringe with the liquid, filling ink into a fountain pen, and many more we experience due to atmospheric pressure. I will make a separate video related to all these points. Here we can see some of the consequences related to fluid pressure. I will try to make a separate video related to all these points too.